So we did our presentation on seismic rehabilitation of earth dams. The purpose of this paper is to present methods available for engineered remediation of seismically deficient earth dams, to review their strengths and weaknesses, to present case histories of the application of these methods, and to draw conclusions about the state of practice. Synopses of case histories are presented by the John Hart Dam, the Sardis Dam, Mormon Island Auxiliary Dam, and Pleasant Valley Dam. So berms and buttresses. First of all, what are these? A berm is a narrow, low mound used to divert water. Its effectiveness is generally limited to a zone that is about as deep as it is thick. A buttress is a man-made fill designed and built to support a weak or unstable slope. Upstream and downstream berms and buttresses are used to increase the effective overburden pressure on the problem material and thus decrease its liquefaction potential. Liquefaction is the sudden large decrease of the shearing resistance of a cohesionless soil. It is caused by a collapse of structure, by shock, or other types of strain, and is associated with sudden but temporary increase of the pore fluid pressure. Berms and buttresses are also used to increase the length of the failure surface, provide a counterweight to limit movement, and maintain a remnant section. It does not reduce the factor of safety during day-to-day operation, and its presence is obviously verifiable. If coarse-grained soil or rock is available, a berm or buttress can be constructed. It's not showing everything.
Oh, and also.
So we did our presentation on the seismic rehabilitation of earth dams. The purpose of this paper is to present methods available for engineered remediation of seismically deficient earth dams, to review their strengths and weaknesses, to present case histories of the application of these methods, and to draw conclusions about the state of practice. There are synopses of case histories that are presented for the John Hart Dam and the Sardis Dam. Berms and buttresses, what are they? A berm is a narrow, long mound used to divert water. Its effectiveness is generally limited to a zone that is about as deep as it is thick. A buttress is a man-made fill designed and built to support a weak or unstable slope. Upstream and downstream berms and buttresses are used to increase the effective overburden pressure on the problem material and thus decrease its liquefaction potential. Liquefaction is the sudden, large decrease of the shearing resistance of a cohesionless soil. It is caused by a collapse of structure, by shock, or other types of strain, and is associated with sudden but temporary increase of the pore fluid pressure. Berms and buttresses are also used to increase the length of the failure surface, provide a counterweight to limit movement, and maintain a remnant section. It does not reduce the factor of safety during day-to-day operation, and its presence is obviously verifiable. If coarse-grained soil or rock is available, a berm or buttress can be constructed on the upstream shell without lowering the pool, although this could be very difficult. Excavating and replacement. Excavating and replacing offers the advantage of providing relative assurance that what was designed has actually been constructed in the field. There are downsides to this method, however, that includes that it is very expensive and operationally difficult. Dewatering is almost always required, and in many cases the reservoir must be lowered significantly. Dewatering is the action of removing groundwater or surface water from a construction site. This process is normally done by pumping or evaporation. This approach is most useful when the problem material is near the ground surface. The excavation and replacement method can also be used after an earthquake to remediate shallow cracking. Another method is in situ densification, which can be used to decrease the potential for liquefaction by decreasing the void ratio of the problem material. In situ means in place and undisturbed. In situ densification is most effective when the material is close to the ground surface and has limited fines content. Some methods include fibro techniques, which present flexible solutions for soil improvement, dynamic compaction, which is a ground improvement technique that densifies soils and fills by using a drop weight. The drop weight, typically hardened steel plates, is lifted by a crane and repeatedly dropped on the ground surface. Another method is compaction grouting, It's a grouting technique that displaces and densifies loose, granular soils, reinforces fine-grained soils, and stabilizes subsurface buoys or sinkholes. The final method is displacement techniques. To date, this method has not been used under an existing dam. Cracking might occur, which could increase the risk of piping. Verification of the amount of improvement and of the spatial variability of the improvement is required in this method. In situ strengthening. In situ strengthening is a form of composite material that is strong enough to ensure stability. Some examples are stone nailing, which is a technique in which soil slopes, excavations, or retaining walls are enforced by the insertion of relatively slender elements. Another example is stone columns, which are dense aggregate columns. And the final example is methods of deep soil mixing, which is ground improvement technique that improves the characteristics of weak soils by mechanically mixing them with cementitious binder slurry. Some of these methods may also cause consolidation and increase the strength of the soil around the feature, but this increase is generally ignored in stability analyses. It's generally most effective when the potentially liquefiable material is confined to a relatively thin layer. In the case of deep soil mixing, it can be implemented for thick deposits. You can also increase the freeboard. An increase in freeboard may be used when the seismic analysis indicates that the dam is marginally stable and/or only a small earthquake-induced deformations are probable. Freeboard is the amount of watertight surface between a given level of lake, sea, or river water and the lowest possible entry point during flooding or large waves. A seismic analysis is a subset of structural analysis and is the calculation of the response of a building structure to earthquakes. The approach decreases the probability of overtopping associated with settlement or slumping of the crest. The final method is drainage. Drainage provides for relief of seismically induced poor water pressure. Some techniques include strip drains, which are used where a water collection system is needed or full area drainage coverage is not necessary or practical. Another technique is stone columns, and the final technique is gravel trenches, which can be used to intercept migrating elevated poor pressure plumes. Extra drains added for remediation will reduce the length of flow lines and thus increase the seepage gradients under static pool conditions. The static safety of the dam will be somewhat reduced and more water will filter through the dam.
One of these dams is the John Hart dam, and it was completed in 1947 on the Campbell River, about 5 kilometers west of the town of Campbell River, which is located in Canada. It consists of a main concrete dam, a power intake dam, and 3 earth-fill parts. A seismic stability analysis showed the large zones of embankments found detonation, which liquefied during an earthquake with a peak horizontal acceleration of 588 centimeters over a second squared, or 0.6 G, meaning that it needed to undergo additional construction to the original dam, so it would be more earthquake resistant. 5 alternatives were evaluated for technical reasonableness, cost, and schedule. But out of the 5 alternatives, the downstream drainage and installation of a permanent cover the dam with a cutoff to permit dewatering and partial soil replacement downstream option was was selected in order to place this cover dam and cutoff wall upstream of the existing embankment. A rockfill containment dike was placed by and dumping in the reservoir. The area between the dike and the dam was filled with sand and gravel, which was densified by vibrocompaction. Also, jet grouting was selected for the cutoff in areas adjacent to and under the concrete structures. After most repairs to the dam were made, the dam crest ended up being raised 1.8 meters by the dike to ensure adequate free board after the MCE introduced movements. Also, an impervious tail zone was incorporated into the new embankment downstream of the critical sliding surface and extended to the upstream face of the dike. The next dam is the Sar Dam. It was constructed in the late 1930s in northwestern Mississippi. Whatever. The dam is approximately 4,600 meters long with a maximum height of 36 meters. The U.S. Army Engineer District in Vicksburg evaluated the probable behavior of the dam during and after the MCE event, having a peak horizontal acceleration of 196 centimeters over second squared. The result of these investigations were not favorable, and some remedial measures were necessary to improve the stability of the dam. After some analysis was done, the dam indicated to have significant strict loss that occurred in three aspects of the dam. The first being the hydraulically placed slip core, the second being the discontinuous layer of silty clay or clay silt located in the top stratum clay. Lastly, the upper 3 to 9 meters of sand shell along the lower section of the upstream slope. There were 6 techniques considered in order to solve these, but the one technique that was chosen to repair the dam was using driven reinforced concrete piles. After this method was selected, an analysis was made at the site to verify the ability to drive a certain size of the piles and to determine hammer requirements in order to drive them. The design of these piles and the spacing is still being figured out. Let's see.
There are still serious gaps in our knowledge. They include soil properties, numerical techniques, construction technology, and internal damage. Soil properties of remediated or composite material are not well understood. In today's engineering, we cannot accurately predict the residual strength of a liquefied deposit, and steady state strengths of liquefied materials can be determined, however. For these procedures to be useful, a good method for accurate and reliable in situ void ratio determination is needed. No rehabilitated dam has yet been shaken by a strong earthquake, which means that no real verification is existent and that the rehab techniques have not been field tested. Simplified programs have been used in examples with centrifuge experiments, but they're not actual results. The static and dynamic interaction between remediated material and surrounding material is not understood, and how remediated hard spots in the foundation will interact with the dam during the earthquake. There are currently 4 computer programs that are developed to predict large deformations: Terra 3, Dynaflow, DSage, and Dynard. But they are sophisticated, complex, and very difficult to use, and the exact values of the deformed shape predicted by those codes are not trusted. Technical guidance needs to be developed so that input parameters like models can be estimated from commonly used field procedures. Much more research is required for this as well. Current methods for in situ densification are sometimes inadequate. Vibroflotation is one example that works reasonably well in clean sands, but not so well if the fines content is high. Dynamic compaction is limited to near surface materials. As shown in the data from this paper, the conventional grouting has not been attempted, mostly because engineers do not have the ability to verify where the grout goes and the resulting composite strengths and dynamic behavior. Jet and compaction grouting were each used once, so all of that needs more research as well. Internal damage is unknown as well. When an earth dam is subjected to an earthquake or fault movement in the dam's foundation with the large deformation, there is no knowledge or understanding of internal damage done. Research for the internal damage and cracking affect the defensive measures against piping that was intentionally designed and built into the dam, which is also entirely non-existent. Most seismic remediation of dams have been conducted after 1971 with the slide in the lower San Fernando Dam. Most problems with dams have been in relation to liquefaction. Seismic retrofits are evenly divided into hydraulic fill dams and engineered dams constructed on seismically poor foundation. Half of the dam cases are operational fixes, which involved simply lowering the reservoir and reducing the risk of failure. In situ improvement is not widely used, mostly because the safety and the results are not easily verifiable. That's not right. This is because the improvement under a dam may decrease the static factor of safety and the results aren't verifiable. Aren't verifiable. Mostly the solution has been to remove and replace the problem material and or use berms, and that's mostly because it's inexpensive for the near surface material, easily verifiable, and does not reduce the static factor of safety while increasing the dynamic factor of safety. All of these show that there's a growing use of post-earthquake deformed shape analyses to evaluate the impact of proposed engineered remediations. Overall, we do not know precisely what the factor of safety will be, and both static and dynamic factors of safety need to be moved in the right direction, so good judgment and common sense are required for all of this.